here we're talking about Chapter 7, the interior components and finish of the building. That includes things like the building services, the electrical, the plumbing, the cabinets, the plumbing fixtures, and the finishes, the insulation. There's a lot that goes on inside the building, and actually more than half the money of building a house is part of the interior finish. It's a big, big deal. Okay, so first of all, looking at building services, there's the drains. That's part of the plumbing. And so out of the drains, there's the vertical stacks if you've got two-story building where the lines are dropping from floor to floor straight down. But then when the plumbing is running at a horizontal underneath the floor or between floors horizontally, it has to have just a gradual slope of about 1/4 inch per foot of run. That said, you've got to have venting that goes on. When you pour liquid down the drain, the air that's in the drain has to have someplace to go, so you have to have vents. And so the vents that you see going up above, sticking out of the roof, that's what we call a plumbing stack or a vent stack. All plumbing has to have venting, and generally within 60 inches of wherever the fixture is at. And there's a few exceptions, but there's tricks that we do in there, but something I can talk about it another time. The other thing we have to worry about with drains is a water trap. And so every single fixture, every single plumbing fixture in your house or your building has a P-trap, a water trap in it, where the pipe goes down and back up again. So you see that for showers and tubs. You see it for sinks of any kind. And then the toilets, they don't show them here because the P-trap or the water trap of a toilet is built into the side of the body of the toilet instead. Okay, so that's the drains. Here's an example of a P-trap underneath a bathroom sink here on the left, and then there's a stub out from a vent stack. And so what you're looking at here is that there's a Y shape, sort of, where that would come from a sink, for instance, like this, and there'd be a P-trap on the end of it. But going up could be nothing more than a vent stack. If it's a single-story building, it could be going straight up to the attic and poking out of the roof. So every fixture has a water trap, what we call a P-trap. Now, and that's another picture I've forgotten. Okay, so it means that the sewer gases, things like the methane gas that's actually flammable, and the sewer flies and the stink and the smell can't get up into your vanity sink. So when you're spitting out after brushing your teeth, you're not going to smell that sewer gas smell. When you pick up a toilet, you're removing that P-trap because it's part of the toilet. And boy, oh boy, you'll smell smells all over the house within no time if you leave that uncovered, that drain. Okay, I digress. The water supply. Here they're showing the solid lines are the cold water lines, and the dashed lines are the hot water lines. And so many of our fixtures have both. A toilet generally does not. It has just the cold water, although some of the bidets will rinse out with warm water, so they might. Okay, that's too much information. Moving on, look at these white PVC pipe plumbing stacks that are coming up, probably all drained. The way they're joining together, it's probably going together straight up to the roof. And because they're so big, they might be for toilet venting from another floor. But the thing I was going to point out here is the metal plates that are nailed to the frames that are around those things. We do that to protect the pipe so that somebody doesn't try to drive a nail in and end up puncturing that pipe and wonder why you have funny smells in your house that you can't track down. But all the plumbing, water supply, and hot water, cold water, the drains, they all have to be integrated into walls, ideally on interior walls. If they have to be on exterior walls, you have to be careful that the insulation is on the other side, on the outside of the plumbing. Well, when you have a big piece of pipe like this in a wall, it makes a lot of sense for the wall to be thicker. So walls between bathrooms tend to be framed in 2x6s to give yourself more room for the plumbing in the walls. And really, the smart way to frame up a house is with thicker walls than a 2x4 framing. For the exterior walls, the smart people frame up their houses in 2x6s or something else. There's some other techniques. You can have a double wide wall that makes a very thick wall and give you lots of room for insulation, but also room for the pipe to be there with insulation behind it properly. Okay, forced air. If you've got a forced air system in your house, you've got to have room for the ductwork moving around through the house between the floors. If you've got a single floor, or for the stuff in Louisiana, very often in the top floor, one way or the other, we very often have the ductwork in the attic. Well, the attic is generally mostly unconditioned space. It's hot up there. Or in the wintertime, it could even be cold up there. Well, the ductwork has to be insulated then. When they're insulated very well, it helps an awful lot with your energy efficiency. A lot of ductwork is just barely insulated, so it's not very well insulated at all, and you're losing energy the whole time up there. But forced air isn't the only system. It's what makes most sense here in the South, because we also need air conditioning, and air conditioning works best if you can run it through ducts. But plenty of systems will have furnaces that only do heat in colder climates where they don't really need air conditioning. More and more places are getting air conditioning anyways, because it helps to control humidity in the summertime. Basically, an air conditioner is kind of a giant dehumidifier. What else? Furnace. You've got to make sure you've got fire retardant material. When you put a furnace and air conditioning system up in your attic, it's got to be isolated by a fireproof material, and that typically is drywall. So we might have a drywall deck that you mount your HVAC air conditioning air handler system up in the attic. Here it's mounted in the basement, and so they had to, on those walls, before they installed the furnace, they had to install that drywall because they wouldn't be able to get to it otherwise. Termination of ductwork needs to be well sealed everywhere before it, even when it's punching through a drywall ceiling or through a wall. You got to make sure that metal duct is sealed up well, so it's not filling up the inside of the wall with air conditioning or heat also, because that can cause other kinds of condensation problems. Radiant heating sounds like a wonderful idea, because the coldest place in the wintertime in any building is typically right at the floor, so you can make a lot of comfort out of that. Well, maybe it doesn't make a lot of sense in Louisiana to do that, since we're going to have forced air for the air conditioning. Well, not necessarily, but probably. But one thing we often do is at least put radiant heating in modern new houses. We often put them right there in the bathroom, so when you get out of the tub or the shower, you've got nice warm floor if you turned it on ahead of time to warm up the toes. And that comfort level really makes a difference. With radiant heating, you have to find some other way to move the air, sometimes with ceiling fans. Here's a radiant floor system where you lay the heating rods, the heating coils or cables in those grooves, and then you can put ceramic tile or something, even hardwood floor on top of this. One of my brothers built a concrete house in the suspended concrete slabs. He literally embedded 15,000 linear feet of PEX tubing that you can push hot water through. And so he heated his house up with water that was actually running through a wood-burning stove when he wanted to, or flipped over to natural gas when he was lazy enough not to want to stoke the stove. There's something called a swamp cooler. And ironically, swamp coolers don't work very well in the swamps. Basically, you run a filter that you continuously keep wet, and these evaporator pads, you allow air to be sucked in through the pads, so they're making the air more humid, but it's also cooling off the air at the same time and removing heat from the air as it makes the air more humid. So that's one of the reasons they don't work very well in the south here, is because we've already got all the humidity we can stand to deal with. So increase in the humidity generally is a problem. But in a very dry climate, swamp coolers, or evaporative coolers would be a more correct term, work very well, and they're way more efficient, energy efficient, in dry climates, that is, at cooling off the buildings. And so especially in commercial outfits, but even some residential sites, they'll go and use evaporative cooling. So this is just a table showing you some of the relative humidity changes and how there's a sweet spot where you can get air temperature changes without causing humidity issues. In dry climates, they actually need humidifiers to increase the humidity, and so this is doing two things at once. But this picture probably shows you better. The air is going through the wet cloth or the wet filter and cooling off the air and it is also collecting dust, so it cleans the air too. And then the excess water is collected, and it can even be pumped right back around again as it cools off. or sometimes you can use that water for other purposes instead, watering the gardens and stuff. So there's other ways to use it. Doesn't use as much water as you might think to go through this process. Okay, so here's a couple of evaporative cooler systems, one up on a roof. This just kind of looks like an air conditioning system there. Then here on the back of I don't know, commercial buildings, they've got different suites and they've got separate units for that. So they are used a lot in dry climates. Air conditioners, of course, we are very familiar with them here in the South. When I moved here, I thought air conditioning was for wimps until I really understood what heat was. It's like my muscle car didn't have air conditioning, and I didn't think it was a problem until I got to Louisiana. Air conditioning generally use refrigerants, and in here I'm using the word Freon. I keep forgetting to change that. The old-fashioned refrigerant was called Freon. Freon R12 in the cars and R22 in the buildings. Well, I just recently got rid of the R22 system I had for my house. In a refrigerant system like this, we have a refrigerant material that's compressed into a liquid, and then it's pushed up into the house to where you have evaporator coils. And so these cold coils, as are written on this picture, we typically call them evaporator coils, where the refrigerant is allowed to evaporate into a gaseous state. And if you think about if you've ever taken a spray can of anything that you sprayed for a while, the outside of the can can get very cold. So there's a direct relationship between temperature and pressure. As you drop the pressure, you can also drop the temperature at the same time. There's a direct relationship between those. And so that little trick of physics allows us to end up with very cold refrigerant that's going through those evaporator coils. And then you blow air through it and you can cool off the house. Well, as you cool off the house, you end up warming up the refrigerant, and as you're sending the refrigerant back, and the yellow lines is taking the stuff back where it then cools off the refrigerant, but it's also compressing it back into a liquid at the same time and sending it up back around in the cycle. So this is how air conditioning works. And when you get to a commercial scale for places like Baton Rouge Community College and high-rises and other university campuses and schools, they will typically get much more efficient systems that require significant maintenance and skills to operate, called a chilled water system. So a chilled water system has a similar principle. It's still using a refrigerant. So if you go back over here to this gray picture, we've got a refrigerant that's running, that's cooling off water. And this treated water, kind of like water in a radiator system for your car would do, but except we're trying to make it colder. And you might have 50-something degree water that you're pumping around and pushing it through air handlers, and then with a pump that keeps the cycle going around and around, and so it keeps cooling off the water. Well, the refrigerant, again, still has to be cooled off because the refrigerant gets hot as it cools off the water. And so there's a condenser water cycle that does its cycle, and it cools off the refrigerant, and that goes outside to a cooling tower, where they let the water run down a series of ladders in the air to cool it off outside. And so it's always relative. The condenser water system is running at maybe 60 and 70 degrees, and the chilled water system is running at 50 or 60 degrees, depending what part of the cycle it's going through. But in the process here, we're able to do the same trick, but on a larger scale. Okay. There's also electrical wiring. That's a big part of any house, is electrical wiring, electrical panels, electrical outlets, light fixtures. Everything about electrical is very involved and very important. The black pipe that you see in the middle of this picture is actually a natural gas line that's being sent out for a backyard grill of some sort. Whereas you can also have some pipe that might look something like that in buildings, some in residential construction too, for fire suppression, sprinkler systems. It's been written in the code since 2012, but many areas are only now starting to require them in residential structures, but they've been required in commercial structures for a very long time. So that's another thing that happens in the buildings. When you're putting in building services, you have to find pathways. So you are allowed to drill through joist in certain special spots. So you've seen some of those requirements listed, that you can't drill holes and notch out beams and joists down near the bottom. Especially, that's the most important, most dangerous place to be notching anything or cutting into any of these joists. You can sometimes drill holes in them like this, like you see here, for this pipe to be running through the joist, but typically only in the first or last third of the span. So let's say you've got a 15-foot span. Well, you divide it up into 3 parts. That's 5 foot in each third, right? So in the first 5 feet or the last 5 feet, you can drill holes, but not in the middle 5 feet. So you get the idea there. You can also see the joists and how you've got joist hangers. And with these eye joists, in order to make the joist hangers function properly, they had to put an extra block of wood in there so you have something positive to nail to. There's a strap that's there in the middle. The big metal strap is a seismic strap that's meant to hold everything together. Maybe they're building this in an earthquake zone. Maybe we're installing this building in a high wind zone or an earthquake zone that you need those metal straps. Now, the other metal parts that you see there are meant to protect the electrical wires. So if you're shooting a nail into the wall, you don't want to change your hairstyle or damage or short out the wires because you randomly put a nail in there. Now, we are supposed to put any holes that we drill for wires in the very center of the wall. Here, the problem is we've got a header of sorts in here where it's keeping the wires closer to the edge. And so because they couldn't be in the middle of the wall, because of that piece of wood that's pushing them over closer to us, that's why they had to have the metal part. So the codes would require that. If you can't be in the middle, in the very center with the holes you drill in a 2x4 frame wall, then you have to do that. And the same thing, you see how we've got some nails, some staples, stapling those wires against the 2x4. Well, that has to be done. They have to be nailed in the center of the wall. So that's something that they watch for. If you go off to one side or another, they could fail the electrical inspection and have to pull those staples and move them over. We can often get away with plastic fixtures in residential construction, but in commercial and industrial construction, we typically have to use metal boxes sometimes, and particularly with industrial construction, we have to use metal conduit, maybe some BX cable, which is kind of a metal woven spun jacket that protects, and it also builds up a protection from the electrical field that's generated with the voltage and amperage. Here's another thing that can go on your building that costs money. If you're going to have a fireplace, and this particular fireplace, of course, it's not finished yet at all. It's just the firebox. Well, it's not even the firebox. I shouldn't say that. It's the box where a firebox will be built. But you can see a clay chimney in the back left corner here. Well, that's coming from down below. Something that maybe you've never had to think about before. But if you got a fireplace like this, that you're going to have a brick, it might be a brick fireplace, but it probably starts off as a masonry structure with brick around it. It ends up, if you're going 2 stories, the fireplace downstairs have to have an independent chimney. They're not all going to join together, otherwise you get smoke coming from the ground floor and coming out of this chimney. And so there's independent chimney, something that you might not have had to think about before. Fireplaces have to have certain tolerances. We see this in here. According to the IBC, combustible wood framing cannot come within 2 inches of the sides or front, or within 4 inches of the back of a masonry fireplace. It's similar tolerances for metal insert fireplaces. And with those metal insert fireplaces, they will have multiple walls of metal with air spaces between them to help keep the air from transmitting. But just like that cute little easy bake oven with a toy little light bulb, you wouldn't think a light bulb could bake cookies or cakes or whatever, but they can. Over time, the heat keeps building and building in a small box. And that's what happens in a fireplace too, is that it keeps building. So if you keep running a fire for a day or two nonstop, the heat keeps building and building, and it can transfer out and actually start singeing lumber. And it can literally burn the building down eventually. So many fireplaces are not built well enough, tolerances well enough, and the code doesn't even give enough protection to run most fireplaces for more than 24 hours. The heat keeps building and building and gets hotter and hotter, and next thing you know, you've got singed wood. I've seen singed framing when I've been up in attics around fireplaces. What could have turned into a house fire, but got lucky enough not to turn into one. Okay. Completing the building enclosure. So let's see. There's 3 ways that heat is lost through a building, and I've talked about this in chapter 6 already. There's radiation, sun shining through your window. That's a form of radiant heat. We're not talking about radioactive radiation, although that's one form. And when you're outside, you could get the ultraviolet rays, which would be a form of radiation that's dangerous. But no, the heat that's shining through the windows. And in a climate like ours, most of the year, having sun shine through the window is a bad thing. It's just going to be heating up your house. So we use reflective coatings on windows to combat that. In a cold climate, actually, you kind of like the sun to shine through the window. Sometimes we size the overhang on the outside just right so that during the summertime you get the shade, and then the sun is lower in the sky in the wintertime, and so then you get the sun. So there's some tricks we can do with that. Conduction, the heat moving between framing materials, is the main culprit, but also if you've got aluminum windows, the aluminum is a direct path of conducting temperature through the building. So that would be thermal bridging as opposed to thermal breaks. When you start putting insulation between materials to separate them to keep the temperature from migrating through the building, that's a thermal break. So one technique is they sell a special higher grade aluminum frame window that actually has aluminum on each side, but it's embedded with some plastic material in between where the glass is held. And that gives you a thermal break, and it makes a very durable, warm window. Convection, though, is the main area we deal with in this chapter, and that's the fact that insulation in the walls keeps the air molecules from floating from one wall to the other. Air in an empty wall with no insulation can float from wall to wall, from outside wall to inside wall, and keep cooling off one and heating up the other, whichever time of year it is. And so when you put fiberglass insulation batting in a wall, it's keeping the air molecule from floating over to the other side of the wall. Fiberglass has only that capability to insulate when it's nice and light and fluffy. The fiberglass, is a horrible thermal insulator. Think about the glass cup that you put in a microwave with some hot liquids. That doesn't stop the heat from going through that glass mug on the handle even. So convection is best combated when you can use some kind of foam insulation. Some insulation that is inherently an insulator to begin with. And so materials like a recycled newspaper material or works, but way better than that are the foam cells. Open or closed cell foam has cells that are trapping gases, not just even air, maybe even more efficient gases in there. Okay, so here's a guy insulating with fiberglass, and he's going to be itchy tonight, or maybe he's used to it, but my goodness. And you shouldn't be breathing in the glass fiber dust either, so you should be wearing some kind of respirator. Okay, so beyond that, fiberglass, again, is only effective when it's nice and light and fluffy. If you've got some cracks to put fiberglass into, you're better off to use something else, some expanded spray foam in a can instead for those narrow areas. Here, somebody's on his stilts and he's putting it up top. And you see the paper that's on this insulation. That's a very common type of insulation for us to use here in the South because it works better having a vapor retarder that is somewhat permeable but does allow the moisture to condense on the surface. So he's got that craft paper attached to it, and that's what we mostly use here in the South when we're using fiberglass batting, because you want any moisture that does get trapped in there to be able to diffuse out over time. Here we're looking at just straight up fiberglass insulation here. When you put plastic there, you're locking in whatever gets in there. It will typically take too long to evaporate out, and so it'll tend to turn into mold. So craft paper is the preferred vapor retarder in general, but particularly here in the high humid South where we run the air conditioners all the time. And run between the air conditioning heat and the high humidity, we can have a lot of condensation problems in our walls. So you don't want to seal them up too tight. Also, the insulation can't be around hot objects. You can't have insulation right up against your fireplace chimney. It's got to be kept away a few inches. Same thing with most recessed light fixtures are leaky, and that means they get hot and they leak air into the attic. And so in the wintertime, you can have moisture condense all around you and soak into the fiberglass and cause stains in the ceiling deck. But the heat can also actually catch the fiberglass or the newsprint or whatever kind of insulation you have up here. It can catch it on fire. Pretty much all insulation that you use in an attic is not fireproof. Fiberglass is a little better, but generally you'd be surprised how well fiberglass can burn. So minimum of 3-inch clearance around this stuff, which means you got this huge area around each of these fixtures that's not insulated. And that becomes a problem. A cold spot in the wintertime in your ceiling, a hot spot in the summertime. Either way, it's bad for you and your energy efficiency. So it's better to spend a little bit more money to have, instead of NIC-rated fixtures, which NIC stands for non-insulation contact ceiling fixture, you should have an IC. Well, I don't think they actually call it IC. I'm doing that for the fun of it. But no, insulation contact rated fixtures allows you to put insulation and pile it up right against there, and with no danger of getting moist from any leakage, because it's a sealed unit to begin with. Important feature to consider. Here we're looking at some ceiling fixtures, recessed light fixtures, that are so bad they're melting snow. You can see it in the snow pattern. And then notice that the plumbing here is on the insulated side of the house. So the insulation is behind the plumbing so that you don't have plumbing getting frozen. And that's particularly important with water lines. The water supply lines have to be on the inside of insulated areas whenever you can. When you run them up in the attic, they should be insulated independently. So they're using spray foam in that section between some studs just underneath that window. Here's some spray foam between the door jamb and the framing. They've got the shims in there and they've made a gap, so they filled that all up with spray foam. Now, when you're putting spray foam around a door or a window, you have to make sure that you're using a low expansive spray foam. They have something that's designed to not be a problem around windows and doors. When you use the regular El Cheapo basic spray foam, it'll tend to push on that door frame or push on the window frame. And if the window and door is closed, then you may never get it open again because it just basically keeps pushing and distorting. Or if you happen to have the door and the window open, then you'll never get it closed again. So yeah, be careful about what kind of spray foam you put in around windows and doors. Those shims that you see up at the top, they've put them in there, but they'll snap them off and make sure they're chiseled away so they're not sticking out before they install drywall. Here's some spray foam, some closed cell spray foam being put on these walls. Now, they don't have to fill the whole cavity, but they're spraying up right up against the walls to fill them as much as they possibly can. That said, it doesn't matter if there's an air cavity on the inside of the wall, because that's going to be conditioned air and generally drier air, especially in our summertime model that we care about here in Louisiana. But it helps to seal up the building. Boy, does it ever. The airspace, the problem is when you have an airspace on the other side of this insulation is where you start having condensation problems. Here's a blown-in cellulose insulation that could be made of newsprint and clothing all shredded up. But we use that in the attics, and you blow in insulation. Well, this is like that too, but they have to mix in an adhesive material that holds all this stuff together. Otherwise, it would settle in your wall, and you'd end up with, 2 feet of gap up at the top where the stuff settled and left that empty over time. So they actually spray it on here with this, and when it sets up enough from the glue that's all holding all the particles together, then before it sets up too much, they'll scrape the wall to scrape off the excess so that you can get your drywall on there. And this is what we do in dry, cold climates, is we'll put plastic sheeting, polyethylene sheeting, what we sometimes call visqueen, which is just a brand name of polyethylene sheeting. So it's called a vapor retarder more correctly, but when it's plastic, it's getting to be more like a vapor barrier, which is okay in a very dry climate because you won't have as much trouble with moisture collecting in those walls, not from this side of the wall. In Louisiana, again, never use polyethylene sheeting on your inside walls. Okay, so with that, wall and ceiling finish. Well, the most common wall and ceiling finish in modern construction of residential construction is drywall, gypsum board, wallboard, sheetrock. They're all brand names. Gyprock is the brand name that I knew up in Canada, but down here sheetrock was kind of like maybe the big brand name. So people call it sheetrock, but it's really called gypsum board or gypsum. This stuff comes in 4-foot wide sheets, and along the long length of the sheet, they will taper the edges. So when you butt the two long sides together, you got a kind of a tapered cavity to put the tape and the mud on so that you can get a nice flat wall, very super flat wall. So it's only at the 4-foot ends when they butt. Well, in a corner, that's not so much of a problem. But if you had to go and butt two areas in the middle of a wall, then you have to build up and make a very wide, gentle, gradual fill so that nobody sees the hump in the wall. So this stuff comes in 8-foot lengths, 10-foot lengths, 12-foot lengths, 14-foot lengths, 16-foot lengths. I know that those are all available. But by far the most common are the 4-foot, 12-foot, and 16-foot lengths. And so when you go to Home Depot, that's probably all you'll see. What we normally do is try to eliminate as many seams as possible. So you try to figure out all the places you can possibly use 16-foot sheets. And then you try to figure out after that, where can you use 12-foot sheets? So depending on the length of walls, you will find that the drywall contractor will try to figure that out to figure out how many of each kind of sheet they're going to use so that they can reduce the seams, and it reduces labor and makes the job better. There was a problem after Katrina with some drywall that was supplied from a source in China where they had in their gypsum material that they were making the drywall, it had a sulfur content that was causing problems here in Louisiana. Other places, dry climates in the country or around the world, weren't having this trouble with this drywall, but it was a problem here because we just have so much more humidity. So it was attacking and corroding wires and plumbing and HVAC, all kinds of things that were going wrong. Big lawsuits involved with that. The trim around windows, in this case, it looks like they're going to finish with some trim. They don't have to, with some casing of some kind that will hide all this, so they don't need to make it all perfect. So very often, the molding that we use, the trim, the crown molding, the door casing, the baseboard, a lot of the times it's hiding other sins, well, other imperfections, the things that didn't have to be perfect by the time you hide it all up. And so sometimes makes you wonder when you see a big, wide crown molding, just how ugly it might be behind that. Okay, and so the gypsum gets finished, and then it gets a paint job, primer and paint, sometimes some other treatments on the wall, but it's a great fire reduction. I know that when I was getting insurance, when I first bought my house, they were asking me questions about how many rooms had drywall and how many rooms had paneling on it, because the wood paneling was of higher fire risks. This stuff is a natural fire retardant material. In fact, in many commercial applications, they'll use fire retardancy, or between apartments in the buildings, they'll have multiple layers of drywall with air spaces between them in order to create a fire retardancy and a sound deadening, because they'll put springy spacers between the layers of drywall so that the sound doesn't transmit through the studs, because sound can transmit in various ways. It can use the wall like a drum and transmit it through, and when you isolate them, you reduce that. And then there's the millwork that goes on in a building, the finished carpentry and trim. And in here, of course, there's a lot of elaborate millwork. It's a pretty impressive picture, all grayed out for us. But this is generally the role of a finished carpenter. And so I mentioned this word already, but the molding that goes around a window or a door on the inside and the outside is called casing. You can call it door casing or window casing. Most of the time it's the same thing, but in some houses they'll get a theme where they'll have a similar casing on the windows, but something that's maybe a little wider on the doors or vice versa. It just depends on the artistic expression going on. So then that's the casing for doors and windows. Up the top at a ceiling, we call that crown molding. And when we deal with the molding this down at the floor, we call that baseboard. And then there can be a little small piece of trim if you've got a hard surface for your flooring, ceramic tile, hardwood flooring, vinyl flooring, whatever. Then we use shoe molding that goes up against the very base of the casing. A little kind of like quarter round shape, but it's actually a little taller than it is wide. So it's not really a quarter round. Anyways, so at the top of the door, you'll have a head casing being nailed against the head jamb, the head door jamb. And then when you get to the sides of the door, we call that the side jamb. Well, you can even get more specific and talk about the hinge side of the door is the hinge side jamb. And then on the side with the striker plate and the latch, we call that the striker jamb. So you can get more elaborate with these terms, but it's all door jamb going on all three sides. And door casing. If it's an exterior door, you'll have a threshold to help seal up the door from the weather at the bottom. So the critters can't climb through and the weather can't seep through. But interior doors, we typically have about an inch or more gap at the bottom on purpose. Because when you have air conditioning or heating, ventilation going on through ductwork, the air gets pushed into the room, but for it to come back, it's got to flow under that door back to the air conditioning or heating system to be reheated or recooled, depending what season it is. So that's part of the air system. When you go and seal up that door at the bottom, you are blocking the air returning, and you'll find that room doesn't cool or heat properly anymore. There's finger-jointed trim here, so that's got to be a paint grade. Nobody likes the look of that to be stained, generally. At least most people don't. So that means that's probably going to be painted. Here's some interior door frame where you can pull staples apart to pull one half of the jamb and the door casing, the one you see at the top of the page on the left, that left picture. That part will be pulled away and installed afterwards, and you can install the whole door from one side and finish it on the other side afterwards. So we call that a split jamb, and it certainly saves on labor. Oh my goodness. But there's a lot more work involved and a lot more expertise needed when you're installing an exterior door, because you're not just trying to install it for privacy, when you're changing in a bedroom or whatever you're doing in a bathroom. You want to also have a weather seal, and that's a whole different level. So this still doesn't look like a weather seal. This is a raised panel door, though, so it's something that I was showing. It's made of separate individual pieces of wood. All these pieces are glued together. Well, not all of them. The raised panels are supposed to actually be loose in little slots, whereas you can see the door casing going around three sides. So yeah, a raised panel door, a 6-panel raised panel door, has maybe 13 members in it when you start counting the stiles, those two vertical outside parts, the mullions, the parts in the middle, the vertical pieces, and then the top rail, the bottom rail, the lock rail, that's where the lock sets at, the other rail, all those rails, and then there's individual raised panels. There's 6 of them, which are usually made up of other pieces of wood joined together. So generally they're not as strong and can't take the weather and the abuse that other kinds of doors. Now that door you see, the white one you see on the left, pre-hung door, there's actually a raised panel door, but it's a fake one. It's a piece of metal that's been stamped out, or sometimes they'll make them out of fiberglass to look this way. But the point is those are strong because they're all one piece of material. You can put a picture frame of casing around a window on all 4 sides, or you can do this. You can have a 3-sided casing window, what we call, where you have an apron. As an apron window. So that bottom sill that you can sit a coffee cup on, or a potted plant or something, the window sill defines the bottom. You have to install that first, and then you get the 3 sides of casing that are installed, and then you have another piece of that same casing underneath that we call an apron. So it's kind of a sill apron window, a 3-sided frame. There's a couple of different names for this, but it's good to understand the detail. This is certainly a little more labor and more material involved than a picture frame window. So it depends on the building. A modern building, you might not want that kind of a look. but in maybe a more traditional colonial sort of house you would. Now here I'm at the bottom. Yeah, on this page, I wanted to make sure you understand that what we call the molding that goes around a window or a door is called casing. Yes, you should probably know that term, sill and apron down at the bottom. The sill is what you can sit your coffee cup on, and then that door casing underneath is called the apron. And then the last bullet on this page, crown molding, up at the top, as I said. If you had an inside corner, you wouldn't do that with drywall, but you could maybe if you had wood paneling of some kind. Maybe have a cove molding for an inside corner. The outside corner, as far as I know, is just called outside corner. You could have chair rail up where the chairs would bump against the wall to protect the wall from being all barked up by the chairs. And then you can have baseboard down at the bottom. Very common. That's more common than anything else. Crown, maybe. Baseboard, almost always. And if you have carpet, then you'll be tucking the carpet up underneath the baseboard if it's wall-to-wall carpeting. If you have hard flooring, such as vinyl, laminates, hardwood floor, ceramic tile floor, any kind of stone flooring and such, and brick flooring, you'll have shoe molding up against that baseboard to actually seal everything up tight and make it good and pretty much keep some of the critters from being able to wander so easily through the rooms. And so you want to understand those terms because you could see them show up at a test near you, at least describing them and understanding what they are or where they're used. Okay, here's some wood strip ceiling, again, for effect. Apparently that's not in style on the Home and Garden channel. It seems like all they want is painted wood, and everything gets painted. As a carpenter, I take offense to that. I like the color of wood, but maybe I'm too old-fashioned. But I just find the bright white a little too boring in modern construction. Okay, but that's me. Here's some painted walls, and they've got some woodwork down at the bottom and some cabinetry. And so I think it's nice when you've got a combination of materials instead like this. Very nice, custom woodwork and stuff. Here it's all painted. They probably had it looking pretty like that, and they had to go and coat it all in paint. And some people just love that. To me, it's just a bit much. Okay, beauty is always in the eyes of the beholder. Beyond that, more beautiful woodwork here, just a few more pictures. And I'm finally going to get to something important here, and that's stairs. The math that we have on exam 3 deals with, the hardest part is dealing with stair calculations. So I'll be giving you some basic stair calculations, not too involved, but significant. And so that's where we're heading to, and you have to know a few terms about stairs first. So here we're looking at some nice woodwork stairs, and there's all open, and that's a good one to use because you can kind of see some of the details. But in this drawing on the left-hand side, we have 3 stringers. The stringers are the zigzag parts where the steps sit on. So that's the structure that you can kind of see on the side because of the picture, because there's some stair balusters, pickets if you will, but balusters is what they call them, that are nailed to those to the stringer on this side and on the other side. But they're typically in a normal residential set of stairs. They pretty much have to be almost 3 feet wide. They actually have to be at least 3 feet wide up where your arms and elbows are swinging, but down at the bottom they allow it to be a little bit less than that because of the trim that you might have down there closing up around the stairs. But it still means a 3-foot span for the tread boards you're standing on, and that's too far most of the time unless your tread boards are very thick. If they're very thick, these tread boards look thick in the picture, maybe, and if that is solid wood, then yes, you could go just with 2 stringers. But most of the time, we'll use 2x12s for the tread boards that we stand on. And so then you're talking about 3 stringers to span that distance, 1 on each side and 1 in the middle. So yeah, there's some posts here at each corner, some corner places, and then individual pickets within there are called balusters. We talk about the vertical rise at each step, the unit rise. We call that the riser height or the riser. And if there's a board there to kick against like there is here, then we can call that a riser board. And then the horizontal part that we're standing on for each of these steps is the unit run of that stair, and that will be called the tread. The tread width, or the boards we stand on, could be called the tread boards, or just call them the treads. But they're what we tread upon, so it's, they all kind of relate to what you might think. In the perfect world, these dimensions would be 7-11, just like the convenience store. 7-inch rise for each step up, and 11-inch run for the amount of step you're from tip to toe that you've got to stand on. Okay, so let's go to this picture. It's showing the stringer from the cross-section here. Over on the far right, it says, let me get my cursor to swing around this, it says total rise. So that's the total rise. I call it the total rise often. It's the total height from one finished floor to the other. So it's the rise or the total rise. And then meanwhile, down at the bottom, you have what we call the total run, or the run, the total distance from the tip of the stairs up to where you step up on the finished floor. So we need to know the total run to figure out if we got enough room to even have those stairs. Because if we don't, we might have to do what they did here and change direction. Have a landing, and then you change direction and have another set of stairs. So sometimes we have to do that. You got a clearance, head clearance of 6'8". That's a normal minimum clearance. That's what the normal minimum clearance is for residential construction. In commercial construction, it's also 6'8" sometimes, and it can be higher. Many commercial doors, like the doors in Baton Rouge Community College classrooms, are closer to 7 feet, which, is only a 4-inch difference, but it does make a difference. So 6'8" is a minimum clearance in general, and that's 80 inches, 6'8". The key things on this page, though, besides total rise and total run, are that unit rise and unit run that you see up in this area up here where I have asterisks in here. The other asterisk I have is about stringer. Yeah, so you have that. You want to make sure you identify this is zigzag 2x12 that's been cut up so we can have shelves to sit the tread boards on. That's called a stringer. And that stringer angle normally is somewhere around 30 degrees in the building codes. 30 to 32 degrees, somewhere in that neighborhood. Back up to the unit rise and unit run up here. The unit rise, we normally call it the riser height and the individual, risers. So how many risers are there? Well, I'm going to count them right here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's kind of like Sesame Street. 15 riser heights, and the last one is stepping up on the finished floor height here, eh? So let me take my calculator just a minute. If those were the perfect staircase, where it's 7'11", 7-inch rise, 11-inch run, then I have 15 risers times 7 inches. That gives me 105 inches. If I divide that by 12, it shows I've got 8 3/4 feet here from one finished floor to another. That's 8'9". And just doing that in my head. That tells you something, but it could be something different. In the commercial code, they don't allow the stairs to be any taller than 7 inches. That's a maximum height. So if you go and let's say you had to make them, let's say you divided this up and found in order to have perfect stairs all the way up and not have any weird steps that are not exactly the same as the others, people will be tripping if you do, So let's say you end up with needing them to be 6 and you have 15 risers, but it actually turned out you needed to be at 6 and 3/4. I'm going to use that. So that's acceptable. So 6.75 inches per riser times 15, and I end up getting 101 1/4. So what is that? When I divide that up by 12, I end up 8.43575 feet. Yeah, so it's it's less than 8.5 feet. Maybe 8'5" or something, I don't know. But anyway, something in that neighborhood. I'm just playing with the numbers here, but I was just pointing out that if you had to go with 6 3/4 inches, and you just blindly kept the tread boards at 11 inches, you know what would happen? The tread boards would be leaning forward. So they would be leaning back towards you, and it would be really funky to walk up on tread boards that have a slope to them. So what we have to do is you increase one number, you have to decrease the other one. And if it's just going a little bit, you can just say proportionally. So if that was 11, we went and subtracted 1/4 inch from the 7-inch number. So that means we need to add 1/4 inch to the 11 inch. So it should be 11 1/4 inches instead, in order to keep these stairs level on a stringer. So that's part of the basic fundamental things about math calculation for stairs, is you want to keep the stairs level, and you want to have as much to stand on as possible. So 11 inches is perfect for our average feet. When you start having very wide treads, that means you got to have really short risers. As you increase one, you have to decrease the other. So the next thing you know, that makes it hard to climb too. So there are limits to this, and there's more to the math calculations than that. But anyways, this is a better picture to use, because you see this stringer right here. It's attached to the header or to the frame of the floor opening, such that your last step, you're stepping off the stringer up onto the finished floor. And that's how 95% of the stringer stair systems are set up. They're almost all this way. So let me back up to the other picture, which is the weirdo thing. The first one I showed you was nicely labeled, but you see how that stringer is even with the finished floor. That's kind of weird, and it's not preferred. That's not a good idea. If you had ceramic tile up there, you got a funky floor out there on the edge that would kind of flex differently, and you'd probably have broken up ceramic tile on an ongoing basis up there because of it. Not the way to do it. So the default way is what you see here. And this is what we'll stick to for all of our math calculations and everything else. This is what you will mostly see everywhere you go with framing for houses, and even for steel structures, for steel frame structures like we have in our classroom building, in the Cypress building. We've got stairs at each end of the building that are exposed enough that you can see how that's constructed if you look at it from the side. And it works this way too. So that's what I'm saying up here at the top. Here, the stairwell header is used as the last riser, instead of what you saw on the previous page, where the last tread board on the stringer was actually even with the finished top. So here, the last step on the stringer, you still got one more step up. And that's the way that you mostly see stairs doing. That's what we're going to focus on only here. So that said, you still have all these numbers in this picture. The angle may be described, and I say that's about a 30 to 35 degree range, actually 30 to 32 generally in construction. We don't vary too much in residential construction or commercial construction with that. With OSHA, they allow steeper stairs on job sites that you're not dealing with the regular public. So for a job site tool trailer or something, you're allowed to have stairs that are up to an angle of 50 degrees, but not in the building codes. That's not what they allow there at all. So the unit rise, unit run, well, the rise is called the riser height, or the risers. And then the runs, well, if you got the runs, go to the bathroom, right? No, bad joke, I know. Well, the unit runs we call the tread boards, or the treads. So just watch the language. So that's what I've got on this page. Now it's written in writing here, so you should be able to recognize it. Stringer, that's the angle, remember, that supports the steps. That all makes sense now that we've been staring at those pictures. The riser height, or the riser, that's the unit vertical rise. Or if you're talking about the boards that are actually nailed vertically there, they're called the riser boards. Eh? And then the tread, or the treads, that's the unit horizontal run, or the member that forms that step that you stand on. It's the board that we tread upon with our treads of our feet, right? So that tread works well with that when you start thinking about it in those terms. You got to find ways to remember these terms. The rise, when we just say rise overall, and we just say rise, well, we're talking about the total rise. I try to keep using the word total next to rise when I mean it, just to distinguish it and not confuse people, but it could just be written as the rise, because then we're talking about the total height from one finished floor to the other. But if you have a landing halfway between one finished floor and the other, then we're talking about individual floors. So then the rise would be going from the ground finished floor up to that platform, that landing that's halfway up or whatever it is. And that's a rise. And then from that landing up to the finished floor up top, well, then that would be another rise. And so you can take them as two separate math problems and work them out independently. And then the run, that's the total run, the total amount of space that the stairs take. Sometimes we have to calculate that out ahead of time so we can just figure out whether it's doable when you're trying to figure out where you're going to put stairs. If you're designing your own building, your own house or something, sometimes when I've been doing the math on that, I figure out it's just not possible to have a straight run of stairs. We have to have a landing. Or sometimes it's because of the head clearance. If I go back to this picture right here, the head clearance, sometimes that's the problem. You got a big beam that's just not going to allow you to have stairs there, so you have to change direction and maybe have an L shape of stairs with a landing so that you turn direction so that you can still have enough head clearance as you're going down into the next floor. Okay. So yeah, railings with posts and balusters, they keep us from falling off these stairs, of course. The guardrails of the stairs, really, they're a very important safety feature. Sometimes we have solid walls around the stairs. We box it in. A lot of older homes will do that. In modern times, we like everything to be open. You want to make sure all of these terms that you can recognize them from the figures we've been looking at here, because these figures either one of them could show up at a test near you. So make sure you spend some quality time. This is a tan picture. Exam number 2 probably is dealing with this picture, I think is what I remember. And I think on our learning outcomes exam near the end of the course, I think I used this picture. Now, there's some stairway math here that I've got at the end of this presentation. I think in the interest of having a separate thing, I'm going to stop here. No, it's here. You can go look at it in the presentation. And I'm kind of describing things in here along the way in the next few pages. And I'll go through some of this math for you, but I'm going to do that in a separate video. So yeah, the math is here. You can freeze frame the video if you want to look at it, but I will also have it in a separate video. And you have some of this stuff worked out in the study guide too. In the study guide for exam 2, I've worked out some stairway problems there, but I'll do that math as a separate video. So that's the end of this chapter 7 otherwise.